Hey guys, what's up? Here at the Lightboard, something new for me, exciting times, to talk a little bit about working up your data to make meaning of it in terms of what we've been talking about in your lecture portion of the class, Chem 320. So we're going to be getting into a few things. We've got the basics of electronic structure. What does that even mean? And how does it apply to the project you've been doing? We're talking a little bit about some d-orbital splittings. You're going to get into that further in class in the last couple of weeks here. And then we're going to fill it up with some electrons, think about how that applies to our Evans method data, how it applies to our UV-Vis data, and how it applies to our CV data. So let's start with electronic structure. We have complexes that you all made in lab, metal, dichloride with a DPPF ligand. I'm going to tell you that DPPF is, for all intents and purposes here, about equal to what we'll call P2, right? This is a diphosphine ligand. It's PR3, two of them, meaning that we can basically summarize the coordination sphere of our coordination complex as MCl2P2. That gives us our phosphorus in 2 spots and our chlorine in 2 spots. This is 4-coordinate. A 4-coordinate complex. So if you think about some of the Lewis structure, VSEPR theory work that we did, the 2 possible limiting geometries for a 4-coordinate complex would be square planar and tetrahedral. So what those electronic structure geometries look like, the way that the molecular orbitals stack out when you go through the whole molecular orbital theory analysis, you have 2 limiting possibilities for your square planar complex. Your d orbitals, the frontier orbitals, the ones we really care about for what we're looking at, take an arrangement like this. It's 3 under 1 under another one, or 1 over 1 over 3. This top one, I goofed up. Top one is x squared minus y squared. The dx squared minus y squared orbital. This is the z squared orbital. And down here, in a degenerate set, we have the xy, xz, and yz. This is assuming that the chlorines and the phosphines act the same and have the same amount of ligand field. We'll make that assumption. It's easy enough. In a tetrahedral case, on the other hand, we have a much different splitting. We have 3 over 2. And here, it's those bottom 3 are now the top 3, xy, xz, and yz. And our z squared and x squared minus y squared show up there on the bottom. So those are our 2 limiting possibilities. And we, in the lab, are going to try to figure out how you get either this one or that one, and how can the data that you collected actually tell you which limiting case you're closer to. So the first thing you'd have to do is fill it up with electrons and then think about it, right? And an easy trick you can do that for any M is to think about how many d electrons it has. The frontier orbitals of any coordination complex are almost always the d orbitals, meaning we can take the 500 orbitals that might be part of our basis set in our molecular orbital theory problem and distill it down into just 5 simple orbitals. You're going to hear more about that in lecture. Takeaway is, once you know the splitting patterns, and here we have the 2 possible ones, the derivation of those should be something you talk about in lecture. All you also need to know is how many d electrons are in the complex. And the d electrons you can get from the group on the periodic table minus the oxidation state. Gives you your d electron count. So let's try an example. Say we made an iron complex, iron 2 for specific. So for an iron 2 complex, iron 2 plus, iron is in group 8. Go check your periodic table. You'll find that's true. So iron is group 8. Minus 2, because it's a 2 plus, that's the oxidation state. That gives us a D6 complex. Sweet. That leaves us needing to then fill 6 electrons into our 2 possible geometries. So if we fill 6 in on square planar, we'll want to maximally pair as many as we can. And if we do that, we see that a low spin D6 iron 2 complex in the square planar geometry is going to have all paired electrons. If I put them in a tetrahedral case, on the other hand, fill them following Hund's rule. Look at that. 2 unpaired electrons. We figured it out. That's how you use data to figure out which geometry you are in, even without having a molecular picture. Because unpaired electrons have a magnetic moment. All paired electrons do not. Diamagnetic. Paramagnetic. Excellent. And we can actually use the data we got in our Evans method to figure that out. That's coming next.